occultation is a little bit about the history of started timing occultations just using a stopwatch and a little 2.4-inch refractor. But then I've, of course, evolved a little bit over the years. I should have brought the 2.4-inch refractor. It's sort of a historic thing, but it's so beat up and sort of an embarrassment. But maybe some history. Okay, next slide. Okay, this is the slide I've shown many times before, but since we wanted to go back to square one to let some of the new people know that there are. This just shows the basic geometry for lunar occultations. As the moon moves in its orbit around the Earth, it casts a shadow of some star that's at some relatively infinite distance to the upper left, and so as the moon moves, then the shadow cast on the Earth moves across the Earth's surface, defining a region of visibility of the occultation. But then there's also motion involved. So an observer, for instance, at position A here is just, the shadow is just reaching him at this particular time, him or her, and the star would be disappearing, and then when the shadow sweeps over him, the shadow will intersect on the other side, and then the star will reappear. So the observer at A sees the star disappear and then reappear, and during the waxing phases of the moon, between new moon and full moon, the disappearances occur on the dark side and the reappearances on the sunlit side of the moon. And that sequence is reversed during the waning phases when most people sleep, but during the early morning hours, during the waning phases of the moon, the reappearances are on the dark side. And of course, for only the very brightest stars can you see them on the bright side of the moon. So most of the events we observe on the dark side. Finally, an observer at B, other people who are outside the path see no occultation, such as at B, the moon would appear to pass south below the star. So this is the moon actually is moving in the sky relative to the star background, but we show the, just say, well, the moon's much bigger in the angular size, so the star moves across relative to the moon. We show a plot relative to the moon here. But the very interesting thing occurs if you happen to be right along the edge of the path of visibility of the occultation. For instance, observer at C at the northern limit of the occultation. And in that case, the path of the star is just tangent to the moon's disk. And we'll show more how the star disappears and reappears then multiple times among the mountains and craters along the north or south edge of the moon. Next, and I'll show some videos. I'll do that during the lunch break, really illustrating some of these events. We have some pretty nice ones we've gathered over the years. The whole idea of grazing occultations, I didn't think of it. And people in the 1950s, they published predictions in Sky and Telescope of what we call total occultations, just ordinary occultations where the star would disappear and reappear, and they had predictions for several stations. I was observing just a few months after I got my first telescope, this 2.4-inch refractor, and observed this occultation of a 6 magnitude star, Beta 1 Capricorn. It's a white double star, and so this is the fainter component, and I observed it disappear, and this is the occult view of that prediction using our current software, showing how you can portray the events to see. This is especially important for reappearances because you have to know where to look to to catch the reappearance or to center your video field if you're using video. But anyway, I duly noted this event, and in those days, actually, it was a little later that I started just using a stopwatch and timing. I got one in here somewhere. I'll pull it out later. But you just see the star, and then as soon as it disappears, you press a stopwatch, and then normally, often for the visual observations, you'll have a time signal, which WWV time signal. I'll talk about that later. To get an accurate time base is important. But anyway, so this was the first star, but then the second star was also predicted to be occulted. But I kept watching, and next slide shows what happened there. I was expecting it to disappear, and it didn't. It just got closer and closer to the edge of the moon, and then passed right over the mountains along the southern edge of the moon. And it was really, it was a bright third magnitude star, so it looked really neat. And I was totally amazed at this sight. And I could actually see the moon's motion. I never really thought of that before, but to actually, see a celestial object, this huge, satellite moving relative to a star, from second to second, I could see it was changing. And as it passed over the Leibniz Mountains, the very large mountains at the southern edge of the moon. And so I saw this happen. I said, well, why didn't the star disappear? It was predicted to disappear. And then I finally thought that the star had disappeared north of me. And the prediction I was using was from a station that was 200 miles north of me. And then I checked, and there was another station in New Mexico, Arizona, which is about 400 or 500 miles west of me, or southeast of me, I mean. And there was no prediction for that. And immediately it occurred to me that about the geometry I showed before, and that I was just on the wrong side of the southern limit. and I saw how the star was moving among those mountains, just above those mountains and craters, and I said, darn, if I had only been a little bit farther north, I would have seen the star disappear and reappear among those mountains and craters. And so anyway, I thought, that was such a neat thing, and darn, I wish someone would predict where those paths were. But I was just a kid then, and I said, I'll never be able to do anything that complicated. Anyway, next slide. Anyway, this is a prediction. The black dot shows where I lived at the time in La Cañada, where I grew up in Southern California. And this was an old map, but it was produced in the 60s, so there were actually some freeways built that didn't exist in 1957, but you can see the predicted southern limit or the actual southern limit over the San Fernando Valley, and if I'd just known that, I been able to pester my parents to say, can you drive me up to Tahunga and we can observe the graze. But anyway, next slide. Anyway, I saw this. It looked like a spacecraft flying over the moon, I thought, when I saw well, it turned out 26 years later, I computed the trajectory for flying the Third International Sun-Earth Explorer, the IC-3 spacecraft, over the moon, and we used a gravity assist that resulted in the first comet flyby of Giacobini's Inner in September 1985. This just shows a rotating plane, an ecliptic plane view of the Earth-Sun rotating, the Earth-Sun line fixed, showing how the slingshot effect of the moon sent the spacecraft into a heliocentric orbit. So next slide. This just shows a close-up of the passage behind the moon, and the next slide just shows an artist's view of the spacecraft doing that. Anyway, After 32 years, though, I mean, that sent the spacecraft into heliocentric orbit, but that's another long story. But it's not over. After 32 years, the spacecraft is coming back. And NASA expressed no interest. They had no funding for it. You know, we have enough trouble funding the Mars, you know, rovers and all these other ongoing projects. We can't be bothered with this satellite coming back. You know, so some people in California got this idea. Who they had done a project to revive the Goddard's archive of Lunar Orbiter photography, to put that online in a modern system and everything, and scan those old photos and all that. And so so they decided, well, let's set up a IC3 reboot project, and they did a crowdsourcing to raise money to buy some transponders would be needed to communicate with this satellite, and they actually succeeded. We hope to do a lunar swing-by on August 10th. The spacecraft will be in the Earth's vicinity, and if we do it right, we can. But we need to use the spacecraft's propulsion system because the current trajectory misses the moon by about 30,000 kilometers. I mean, that's pretty good targeting from 32 years ago, but not good enough to capture. So we have to be within about 50 kilometers above the moon's surface or so. And so we tried to do a maneuver earlier this week, and it failed. There was something wrong with the pressure into the spacecraft or something, or we think now that there was some hydrazine, so some of the fuel probably boiled off. It was too warm and formed air bubbles in the fuel line. So there were some similar problems with the spacecraft at Venus that they were able to solve. So we haven't given up yet, but we're not sure we're going to be able to pull this off. That's right. Yeah. Formal McDonald's out at Ames in Sunnyvale, California. So that's where I'll be on August 10th with those people. Next slide. Anyway, as I said, 5 years later, after having some college courses and so forth, I decided I could possibly observe predict these occultations, and so I did calculate the last Aldebaran graze of the 1959-1962 series occurred on March 12th, 62. And so I set out to calculate that weekend, and it was a harder job than I thought. I was just using Marchant calculators and doing this all by hand, and tables of sines and cosines. At least I didn't have to use logarithms because the Marchant calculators then could take, do multiplications and divisions. In the earlier calculators, they could only add and subtract. And you had to, but anyway, less than 2 hours before I'd finally calculated enough points to know that the path was south of Berkeley. I was at the University of California then, and that the path, the map really doesn't show up too well in this view, but here's Santa Cruz. It was the southern limit was, I predicted, north of there, and a graduate student I convinced to drive. I didn't have a car at that time, but we got to Palo Alto, where I said, okay, the stars disappear. I was looking up with binoculars as we were driving across the bay at the bridge to get closer to the path, and I saw the star disappear, and so I quickly set up my 60-millimeter refractor, and I saw Aldebaran reappear on the bright side of the moon, and I was looking in the right place. But it was very interesting. I didn't expect it, but I could see that the star just came out like a drop of water. It was a gradual event, very noticeable over a period of a second or two, and I was close enough to the southern limit to actually see the star's angular diameter. So that began the chase for grazes. Okay, next slide. And finally, the first success didn't come. It was surprising in California. You expect clear skies all the time. Well, the next six events I predicted were all clouded out. So even there. But finally, this success occurred in Southern California when the fourth magnitude star, 5 Tori, was occulted. It was a bright limb event, and so there were 2 observers, and one had just a small telescope with a wide field of view, and the glare of the moon wiped him out. But Leonard Kalish actually saw the star disappear and reappear multiple times, confirming my predictions at least. He didn't have a timing method or anything, but at least he actually drove up and saw it. So he was the first person to actually travel to a graze path and get an at least see and confirm that the event occurred. Anyway, next slide. This was my first graze that I observed then. It was just a year after the Aldebaran one, March 63, March 31st, with a 6th magnitude star, but it was on the bright side of the moon, just very close to the cusp though, so I was able to tell that the graze prediction was, although the bright limb, the star just merged, I couldn't get any real timings. At least I saw for myself that the predictions worked. In fact, 2 nights later, there was another graze that was just south of Berkeley in the Bay Area, and I also observed that one. That was also on the sunlit limb, but it was a brighter star, so that I could actually see a couple of events there. Next slide. The first really successful dark limb graze was on September 8th, 1963, where we set up 3 stations near Davis, California, and finally we were able to make good timings. So I was working in those days with the Moonwatch teams that were observing artificial satellites, and so I was familiar with a way of accurately timing things visually. And they didn't have video in those days, at least anything that we could buy, and so there were a lot of people out with stopwatches, and by then we had actually had the new technology of using tape recorders, to record we could call out the events, we could record WWV, and so that turned out to that we actually used that for these observations. Anyway, so switch to the next slide. This just shows the first graze map that I published in Sky and Telescope, which generated quite a bit of interest because it was a nice bright star grazing well on the dark side of a 67% sunlit moon at a convenient time in the evening, and it turned out to be clear over most of the country. And you mentioned the David E. Laird Award. Well, David E. Laird was right in that area. You can see how he got interested in this. And anyway, go to the next slide. The graze, this just shows a schematic showing how this is from the graze observer's hand, or the Iota occultation observer's manual that Richard Nugent has put together. And unfortunately, the graphics don't really show up very well through this. It's a little disappointing. I wonder if we might be able to. Yeah, they do. We ought to have a side view where we show the actual presentation through here. We might do that for the afternoon presentations if we can. And you see the crummy things, and we can see the good ones. Anyway, if you could see this shows the edge of the moon and showing how there are the mountains there, and then it projects onto the Earth's surface the jagged edge of the moon, and it shows a road here. This is a map of Texas showing, because that's where it's from, and there are observers then set up along the road, and then different ones see different paths behind the moon getting different chords. So this just shows the general idea. You can see it slightly better than that. So So how, or probably 2 north has a miss and so forth. Next slide. Anyway, for visual timings these days, you can actually use the web. You can use the www.time.gov, and it'll give a display where the seconds change every second, and it'll tell you what the accuracy is. I mean, it has a way of figuring out the signal going, through, whatever it goes through, and taking that into account. So it's typically accurate to 0.2 of a second or so in most places in the U.S. If you get overseas, it's it degrades and can't be really used too well. But for mobile and video use, though, you want something a little more accurate than you can get from the web. Although there's some ways of getting accurate timing on the web, you have to be very careful to do that, though. The easier way is to use a shortwave time signal from a shortwave radio. Is the cheapest to get a really accurate time base, and you have to have one that can receive at 5 and 10 megahertz. Those are the best frequencies at night. Usually 5 is really the most important, but 10 is often best during the dawn and twilight hours. And that can be the case if the transmitting station, which is in Colorado, is in twilight and you're in complete darkness. 10 will probably come in better than 5 at that point. But if it's broad daylight, then 15 becomes important. And sometimes occultations can occur during the day that you can see, that you can observe. Not too often, but they do happen. So anyway, the observer's manual that explains all this is available at the website shown here, so you can get these presentations from the meeting website. Next slide. Let's see, where is that? Just, okay, I don't know. Oh, that's not even there. Okay. Anyway, this is the second page of a 2-page article about that 1963 October occultation of Zeta Tori, showing how, the diagram was there, showed this was the expedition from Dayton, or from Columbus, Ohio, where they set up 4 stations north of Columbus. The Columbus Moonwatch team did this, and there are 4 observers. One of them had no occultation, and you can see the timings of the others are plotted there. And then they gave the timings and the map. And from this, Tom Van Flandern at the Naval Observatory was able to reduce the observations and showed that there was a shift in the prediction from what was expected. They thought all of these things were figured out to 1/10 of a second accuracy, but there was an error of 3/10 of a second. And they said, well, how can that be? But the observations don't lie. That piqued USNO's interest in occultations and started the collaboration with Tom Van Flandern and myself to promote grazing occultations among the amateur astronomy community. Also where I met Joan, who was working at the observatory then. Next slide. Anyway, these are the methods of observing high-speed celestial phenomenon. Just to cap, all methods need an accurate time base, UTC time base of CHU, WWV, or GPS, whatever you can get to provide the accurate time base. Then the different methods of visual is that has been used in the past is eye and ear, where you listen to seconds ticks from the shortwave radio. And in earlier days, they just used ticks from a pendulum clock, seconds ticks that But then you have to mentally interpolate when the event occurred, and you have to also keep track of which second it is. There's always the which second problem if you have a timing system that relies, for instance, on the 1 pulse per second. You have to know which second it is. Then slightly easier to use by most people is to use a stopwatch then, rather than try to mentally interpolate. People who really figure out the eye and ear method swear by it, saying it's much cleaner, but because then you're kind of eliminating the reaction time problem that you have to apply for a stopwatch. But if there's more than one event, with a stopwatch, you can do it. We figured out a way of using two assistants, one to read the stopwatch and the other to write down the times as the assistant called them out. The observer would say D, and then the person watching the stopwatch would say 15.5. And then the other person write it down. But then we quickly figured out that it was much easier to use a tape recorder and record the calls of the observer, and then you didn't need the assistants. And then the next step up, though, after visual with tape recorder is to go, or with any audio recorder, you can use a camcorder in audio mode. Tape recorders aren't that common these days. There are small digital recorders you can buy, but if you don't have a video system, you're encouraged to certainly get these things at places like Radio Shack. Also mentioned then video system. We started doing those in the 1980s when the equipment finally became less than buying a car, and then finally the equipment became small enough that you could actually take it on an airplane, but earlier than that, high-speed photoelectric systems were used at the major observatories, and these are a few amateurs do that because it's good also for light curve observations of asteroids and different things. But nowadays, CCD systems are more in vogue by amateur astronomers. And there's the drift scan method you can use with these things. And it's too bad we don't have very many people in the US doing these, but there's lots of people in Europe. Lots of the amateurs are doing astrometry with CCDs, and so there's a lot more activity in Europe of doing occultations using the CCD drift scan method. By amateurs who have that equipment, they don't want to buy video equipment too, but they've got something that works and gives fairly good results. But video equipment has come down enough that more and more people are getting it, and of course that's what we're encouraging. We've talked about remote sites, so I'll mention that a little bit, but I have a whole presentation so I can say more about that tomorrow. Next slide. It just shows a typical visual observation showing the time cube that receives shortwave time signals, it's unfortunate that those were very handy to use, but they discontinued manufacturing them in 1983. You can maybe still get them on eBay, but not very common. And then this shows a cassette tape recorder and a GPS and some eyepieces. Just that's the basic idea. And now showing using the finder scope there. But next slide. This is just items for video observation. This is a little bit old, but just showing the different things that you need. The PC-164C camera, which is a KBC from the Korean company. You can still get those cameras, and they're less expensive than that now. But the Super Circuits now sells the PC-164C EX2, although they're even trying to phase that out in favor of the DNR cameras, which we'll be talking about later. PC, the older one, is actually better because it doesn't have these micro lensing things, but it's less sensitive. So for getting more occultations, you really want the EX2, and that's what we usually baseline for our observations for video. But if you're at a fixed observatory, really the WATEC cameras are a little more expensive, but they're better quality, get better records. Anyway, for if you're using WWV for the time base, you also need a microphone with a preamp that otherwise you can't record it on the video. Just a regular microphone you plug in, you won't get it. It has to be boosted, and so there's a so-called PA3 microphone and tab adapter, which is the tab adapter allows you to use a 9-volt battery with it's a very small thing, and that'll allow you to record WWV on the video. And then you need some 12-volt battery for the camera, and I'll show examples of those, and connectors, of course. And then there's a 2.5-inch to C adapter. The C adapter is the standard video, but you need to put the camera in a eyepiece holder, and so Adiratic Video used to sell that. Now the Night Owl in Pennsylvania sells those. Anyway, if you're using a Schmidt-Cassegrain telescope, we recommend the Meade f3.3 focal reducing lens, which fits both Meade and Celestron. It doesn't work for some Celestrons, but it does for most of them. And that gives you a wider field of view. And an input-capable camcorder or portable 9-inch TV VCR combo combination, those used to be pretty cheap, but they stopped manufacturing those several years ago. And now instead of what we use now, we like are the Canon camcorders, which record directly to a digital format on a tape. Unfortunately, all of the digital recorders these days use compression, and you lose sensitivity, and so unfortunately, they're just not very suitable for our purposes. You can use them. Some of them, I have some examples, but if you can get the Canon ZR camcorders, which have input capability, there are just certain models that do that, then you can still get those on eBay, and they work better. And the best yet, though, these days is to go directly into the computer if you're at an observatory or something. So these talk about the shortwave radio is the cheapest way to get an accurate time base, but using an Iota video time inserter or other GPS video time inserter then will timestamp every frame, and it's much easier to analyze the observations. Next slide. It just shows some telescopes. This was actually a remote grazing occultation where we're using tracking telescopes that you could track over a period of, Schmidt-Cassegrain telescopes that could track over a period of half an hour or so. You could set these up accurately enough to do that, and for a graze of it, for asteroid occultations, it doesn't quite work. Anyway, next slide shows some of these in detail. This was sort of a cheap video system using a combo unit, and this is a PC23C camera, which is a less sensitive camera, but it's a cleaner one. It works better for lunar occultations than the more sensitive cameras that we typically use for asteroid events, like the WATEC or PC164C. So I like to use this older camera. I think you can still get them on. Well, I don't know, not the 23C. They have a color camera, though, the 33C, that you can, I think, still get. But anyway, showing a battery using, we have better, little more compact batteries that I'll show you later. But this shows the focal reducing lens, and this, of course, the adapter is in the sleeve. You can't see it in the eyepiece holder, and connecting the camera to it. And then there's a cord, that white cord here, that goes to the back of the combo unit to record the video. Next slide. And this just shows the same thing, but using a camcorder and a Waytech camera, which is a little more expensive, but that's let's see, the small 12-volt battery is not shown, but I have some here. Next slide. This shows a Carryon system, and this just has everything nicely labeled that Richard Nugent set up using a 4-inch Meade, showing he had sort of similar connections. Here's the little battery pack that you can get, the basic thing from Super Circuits, the 8-cell battery pack, and then you just populate it with AA batteries. That you buy fresh ones or use good ones. And then showing the camcorder and the WWV time signals. But he's updated this, and you see the next slide. This shows his current system, where he's using a digital recorder instead of the analog camcorder that he had before. It has some compression, though. It's it still can be used, but I would prefer the ZR camcorder to give slightly more sensitivity. But he has the video time inserter. This is an Iota VTI. You have a couple of things, feed on it that you've added, it looks like, and you have a GPS, external GPS, although the Iota VTI has its own built-in GPS, so you don't absolutely need that unless you're an observatory dome and you have to get outside the dome. But this is for carry-on use. You don't worry about that. So it's, anyway, you can fit all that in the backpack and carry on. Next slide. But if you want to have more than one of them, then it takes a little more effort. So Scotty Dagenhart, had this idea of trying to miniaturize things as much as possible, and so he came up with the so-called Mighty Mini. And here's the Mighty Mini, which is just part of a binocular. It's cut off. I'll have some pictures of it, but it can record stars down to almost 10th magnitude. And then the slightly bigger MIDI will go down to a little more than 11th magnitude. So, and then finally we have the Maxi, which it's a little hard to get on an airplane, but it can. I have two versions. This is the mount that Scotty came up with, slightly more compact, but this is an easier to use mount, which costs a couple $100. The binoculars, of course, are pretty cheap. They're like $36, and you cut them in two, so it's like $18 for each one. The optics are cheap. The camera is more expensive because it's of the order of $100. And then, this is $120 from Orion, the 80 millimeter, and the 120 millimeter is $300. So those are the costs involved. Next slide. I just want to mention, because we aren't going to mention it in other parts of the lecture too much, about another activity that Iota has some experience with, are impacts of meteors on the moon. In fact, Iota was the first one who got confirmed video observations of lunar meteor impacts. And it was during the 1999 Leonid meteor shower that happened, where I recorded with a 5-inch telescope. I was observing about 40 miles northwest of here, in Mount Airy, and successfully recorded about 12 events. And it was 3 hours. It was about 3 hours. So I think there was about 2 hours when the activity really occurred. And I recorded the events not knowing I was getting anything, of course, in real time. There were some lunar occultations at the time, too, and I recorded those. So at least I'm getting that. This is sort of, I didn't think, at the time they thought that these things would be like 6th magnitude, so it'd just be barely visible or so. But it turned out the brightest ones were 4th magnitude. And it turned out that Brian Kutnick was observing, and he saw my call to get video observations, but he said, well, I don't have video equipment. Is there any point in observing visually? And I said, well, if you can't get video, we may as well use a tape recorder and see what you can do, And it was a good thing he did, because then he instead of just recording and not knowing what you're getting, of course, when you're observing visually, you know right away. And so he saw one of these bright events and timed it, and said, and then he called me, or he sent an email, I think, and said, hey, I got an event at this time. Do you have it in your recording? And so I was really surprised when I played my video back, and there it was. Anyway, the next slide shows. Yes, yeah, he was in Texas, and I was in Mount Airy, right. And we got we also got recordings then. David Palmer was using a telescope similar to mine here in Greenbelt. He worked at Goddard. And so, although I lived only a mile from him, instead I went to a darker site, 40 miles away. And but then also we had observations from Mexico. Pedro Sada Valdez observed from Monterey with an 8-inch telescope. He recorded a couple of them, and Rick. The fellow in San Antonio, he got a couple of observations too. So we did get some wide separations and good confirmations. Now this is one of the best ones, though. 2 years later, there was another one with a thin crescent moon. So the moon wasn't up above the horizon that long, and the moon was only about 3 degrees above the horizon at this time. It was just a nice, clear night, and I was observing at Laurel, where I could get a low enough horizon to get this. But this is the frame before the impact, and you can see the dark side of the moon. The next slide. And so there's the impact, right? Whoops. Okay, well you slipped too far ahead. Go back. Yeah, there it is. And so this was. This is my recording of it, and you can see some of the features, so we were able to identify where on the moon it hit. It was confirmed by Tony Cook, who was recording from Arlington, Virginia, and he was up in a high-rise, sort of similar to Elizabeth's, and where he could get a view out the balcony. I think he was at a friend's there or something, and he could get a view of the moon. And Roger Venable also recorded this in Augusta, Georgia. Next slide. Well, actually, this was earlier in the evening. The moon was higher. There was another event that was lower. And you can see this is the next frame. You can see this afterglow still there. And the next one, it's still there in the next frame. But in the next frame, if you look at the next frame, it's gone. so just 3 frames. One frame where it's bright and then trailing off. And there have been better events since then. It got the people at NASA interested, and they set up the recording system. I tried to get APL, say, hey, we got. I was working at the Applied Physics Laboratory at the time, and I said, we got this discovery. Maybe we should put in a proposal and do something. They had 0 interest in it. They sort of discouraged me. I had other things to do, and said, okay, forget it. Now I'll publish this. We'll publish this, and sure enough, though, other people picked up on it, and the people at Marshall now are sort of running the show and have gotten some dedicated 14-inch scopes and things to record these events. They have over 100 events recorded now, including some brighter than what we got just from sporadics. So But one thing during a lunar eclipse, it's good to record the lunar eclipse. George Veros, who lives in Mount Airy and whose house is where I had made the original discovery, he's part of this network now, and he, on an amateur basis, and he recorded the first impact during a lunar eclipse in 2009. Next slide. Okay, this just gives the more information about the different sites. The main thing is go to our main site because it has links to all the others, the www.occultations.org. So the free Iota manual is the next link, and I have a website for local expeditions, and then the Iota site for lunar occultations by Rob Robinson, and Steve Preston's site for the asteroidal updates, and resources for asteroid occultations, Brad Timerson's excellent North American site, and the observation of the general site. He has lots of resources there to get further things. And then the Derek Wright's site for Google Maps for the asteroid occultations is highly useful, with the future events too. Next slide. I think this is the last one or near the last. Okay, this is okay. This just shows a list of some of the video things. We'll show them during lunch, as we can, but we'll show them offline because we won't show them over the web. I don't think we'll be able to. So we can't get them to the server because they're huge files. We do have a couple of them that are on YouTube, though. I have YouTube links, and so we need to go to those if we can. Oh, okay, great. Let's see, I think this is the last slide then. We might try those YouTube ones and then get them out of the way, and then we'll.